very good. Okay, so let's start. So what we were doing, in these last two lectures, was that we first wrote down, so we were looking at how the quantum version of uh, Noether's theorem, what that can teach us about the endpoint functions, how we can look at the changes of endpoint functions, and we hit upon an identity which is called the Ward identity, where we this was 3.17, the box equation was the equation that we found. This particular thing where what had happened was this x was close to some operator which was O1 at x1, so that accounted for the change of O1 under this particular symmetry. So we had this identity, and then what we did is that we tried to see what the form of the Ward identity would be when we're looking at the thing of interest, that is conformal symmetry in this case. Okay, so what we first did was we wrote down a form of what the J's would be in this case. So we went through infinitesimal coordinate changes, and we found out what the form of what the change in action would be, and from there we found out what is going to be the form of jz and I mean j of z bar. So we found that j upper z bar, or equivalently j lower z, was given by tz into epsilon z. This particular thing meant that this was a holomorphic type, and we similarly had an expression for the j bar as well, and that was anti-holomorphic. Once we did this, we sort of plugged it back into our Ward identity, and because we are in 2 dimensions, we could write this del alpha of j alpha in a form which was like this. So this is something that should be familiar to you from complex analysis, and if it's not entirely obvious, just sit down and do it. You would be able to get what this particular identity is. Actually very simple. So now what we do is we plug in this form of the Ward identity, if this form of the J's inside our Ward identity, and we end up with something which is like the thing that I've circled out here. So this is, you would remember, this is, as I stressed before, this is something which holds for any j when d equal to 2, whereby you can actually write down some d alpha j alpha in a form which is like this. Okay, so we have used the fact that in 2 dimensions you would be able to write the Ward identity in a form like this. Now what we're going to do is we're going to specialize to the conformal Ward identity. And for that, as we have seen before, what we have is that j and j bar, the j of z bar and j z bar of z bar. So these actually become just holomorphic and anti-holomorphic guys. So in that case, what is going to happen is this lower equation is just something which depends on z here, and this particular thing will depend on z bar. So what we will find is that this is an integral, right? This is an integral over some j of z into this guy, and that gives you, so this is a contour integral around some circle, epsilon, right? So what are we going to get? What we are going to get is as you know very well, this particular thing. So you invoke our usual notions of complex analysis to read off that this integral is nothing but the residue of the pole of this particular function that you're going to get. Okay, we know when you take jz to be close to this O1, you can expand out this in a series of we can use operator product expansions to expand this out, and this integrant inside will be made up of lots of lots of pieces which is sitting inside this particular contour integral. So what happens if you have something inside? Well, think about some particular guy, and this is some particular contour out here, and you have some poles here. So what happens is that it's the 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 value of the integral, as you know really well, is determined by the residue of the of the pole of this particular this OPE, if you wish. So what is going to happen is that this integral is going to, so the OPE is going to be of a form whereby you can write, okay, let me just rephrase this. So you can write this as we have seen. You can write this guy as some OPE, and the OPE is gonna have terms which are singular terms. So these are the terms that we are interested in. It could have z minus omega whole to the power z cube, z squared, zn, and zn. But the thing that is important is that the word identity is going to pick up the residue of the pole. So this guy, so the z's the jz one op is going to be is going to be of a form like this, and this is the piece that will actually be picked up by this particular integral. Okay, so that's what we were trying to say earlier. Okay, uh, so this so if you put it back into the word identity that we had, so now we have a very nice way of trying to interpret this word identity. So the word identity gives us that the change in O1 is going to be the residue of the OPE, of the 1 by z. So it's going to be the coefficient of the 1 over z piece, 1 over z minus, yeah, I call this sigma 1, but yeah, that's fine. So it's going to be it is going to be the coefficient of the 1 over z minus sigma 1 piece uh, of the OP between j and O1. As we know, as we have seen, j of z is going to be given by epsilon z into t of z. So if you look at this whole thing, then it is going to be, again, is the thing that you need to pull out of this is going to be the 1 over z piece, right? So that, again, so the residue of this whole guy is going to give you what the change in the O1 is. Okay. And similarly, you're going to get a similar piece for the anti-holomorphic piece as well. So in a sense, what we are stressing here is that if you know the OP between an operator and the stress tensor, we know how the operator is going to transform under these conformal transformations. Or equivalently, if you know how the operator is going to transform, we know at least some part of its OP with T and T bar. So that was one thing that we did last time. And the other, so then what we tried to do after that is we tried to understand how this OP is, how you can actually construct the OP from the symmetries itself. So for example, we looked at translations, and for that, uh, the very simple thing is that when delta z is just epsilon, which is constant, in that case what you'll have is just expanding O of z minus epsilon. You get that the change is going to be epsilon into del O of z. So what does that give you? That just gives you the fact that tz with O is going to have a piece which is 1 over z minus omega. The factor in front of it is going to be del O. Okay, so this just follows. I mean, you just insert this. You insert it into. So what you do is you just take, I mean, epsilon equal to I mean constant, and insert it here. So the epsilon goes out. So the t with so this the change here is going to be given by the residue of the t z with the O1. And you know that this delta of O1 is del O1. So now you know that the T of Z with T I mean O of omega is going to be given by T of O by Z minus omega. So that's the, I mean, that's the piece that you're going to get. Okay. Okay, so that's one piece that you can get simply out of I mean out of trying doing this particular thing. When you have del z is equal to epsilon, you can do similar things for rotations and scaling when z goes to z plus epsilon z. And in that case, so I said we try to stress that so this is going to be, so not all operators will have nice nice properties under rotations and dilatations, but we are going to choose a basis such that these operators will transform in this way. Okay, so then your h and h bar are going to be the weights, and the fact that you can expand an operator into a form like this is just so this part of it is just, I mean, the usual translational I mean, so you can just get this part by expanding O of z minus epsilon z. But now you also have this extra bit where you also say that these also there are weights h and h bar under which that these are going to so the form of this is that the terms h and h bar h of o and h bar of o are special to these operators that are eigenstates of dilatations and rotations. So if you do this again by plugging it into the Ward identity, now what you can see is that the Jz is now Z into T of Z, and if you just plug this in, the Ward identity with the T takes a form like this. So what we have been able to do is that we have been able to determine something which is, the 1 over z squared piece, and we have also been able to determine the 1 over z piece, right? So now we define the notion of primary operators, and for so you see that there were dots out here. So these were extra terms that you could have when you're looking at any sort of arbitrary operator. But what we said then that we were going to focus on things called primary operators, and for these guys, so these dots will not be there. So the most singular term is going to be the one with z minus omega, uh, I mean whole to the power minus 2. So this is the leading term. This is the leading term, and the rest of the terms are there. So there are two singular terms, and then the rest are non-singular. So and then what we did is that once you have the form of the OPE, if this 3.24 is something that you have got, then you can then write down the transformations of O under all I mean all sort of conformal transformations. So the infinitesimal form of this is again just you plug back the fact that you have this TOOPE, and you look at this whole object. So what you get is that once you do this, what you need to do is you need to pull out the 1 over z piece. So what you'll get is the change in O is given by h. This is what the change in O will be. Okay, and you're going to get an analogous thing for z bar is equal to epsilon bar z bar. That's fine. So when you integrate this, what you will find is that you end up with something which is equation 3.26, and this is I mean the infinitesimal version as well as the finite version are actually identical to the ones that we had done before. And I try to stress that this in a CFT, one is very interested in the spectrum of weights h and h bar of these primary fields. Okay, these will in a sense be equivalent to looking at a mass spectrum in a QFT, or for and I also said that these weights are also going to turn out to be critical exponents when you're looking at something like statistical mechanics. So that was what we did last time around. And let me quickly pause to ask you if you have some things to ask. Um, Otherwise,
I have a question.
yeah, please.
Yeah, so like the radius of convergence of an OP between two operators is just up to the next nearest insertion, right?
That's right. Yes.
So then, like in this conformal word identity, the contour you're using, you have to
Yes.
make sure that like you're not including any other insertions, only that
You are
one
right. I
operator
mean,
insertion.
what is going to happen is that, yeah. So that is going to be our. I mean, as you would have seen, we will look at this more and more. So what we are going to do is the contour of integration will be these guys actually. So it will be this. Okay,
Right, right,
where
right.
I mean epsilon is not non-zero. You could obviously have something like this and something like this and so on. But
Yeah,
you what you just need to do is you need to choose things in such a way that you're all I mean you're going to sum over all of these guys. Okay, so I mean in a
right,
sense the word identity here, I mean I have just shown it when there's just one O1 here, but you could have thought that your I mean epsilon is not non-zero here, and there is something which is I mean non-zero here as well. For that case you just add these up. Okay,
right, right.
so yeah, I'll try and give you some more I mean examples of this as we move forward, but yeah, that's a rough idea.
But even adding that will be a little tricky, right? You have these poles, so the contours, like when you're trying to add them up.
Yeah, so it'll be something like so this I'm sorry, so let's try and see if this doesn't vanish. It'll be something like this maybe, right? So yeah, I mean I will try and clarify this a little bit more as we go forward. But I mean if you have more than one, so here it was a simple case of trying to do it for one particular operator insertion, but you can obviously do it for more things as well. So it then in that case, so you see that I mean I just took one of these guys here, right?
Right, right.
So instead
Yeah,
of doing that, I mean I could have done it for all of these guys and had a sum here, right? So then
okay.
then
Yeah,
what would happen is that this thing will have a sum as well. So there'll be a sum with all of the
right,
eyes,
right.
I
Yeah,
mean
yeah.
eyes inserted. So I'll try and give you, I mean at least, yeah, if I don't do it here, I'll send you some material whereby you will see it. But it's important to just understand. So once you understand it for the simple one, then the next, I mean the next order ones I mean are reasonably straightforward to understand. But the I mean the what I'm trying to stress is that the broad idea should be clear. If the broad idea is clear, then we would be able to, so we would be able to look at more generalizations, where I mean 3.17 is not just a change in the O1, but I mean change in OI in general. Okay.
Right, right.
Yeah.
Yeah, yeah. Sure.
So,
Yeah.
like,
Okay.
I have a comment.
Yeah.
Uh, uh, so, isn't it the Cauchy integral formula for multiple poles?
Yeah, it is that.
Yeah, yeah. Okay.
So, I mean, instead of one, you just have to, I mean, deform your thing for, I mean, all of those things, right? That is what
Yes,
you do.
usual thing, yeah.
Yeah. Okay. So, right. So we were looking at the OPs with these guys. So what I'm going to be doing in the next bit is, try to make our life simple and look at an example. Okay. So we are going to be doing the simplest example of a CFT. This is going to be a free massless boson. Okay. So the equation, so the action is going to be, I mean, del mu phi, as there is no mass term here. I'm going to put a factor of g in front of it. This is going to be specified for the moment. And this next part, I'm going to be going a little fast, in the sense that we're going to calculate the propagator. I am assuming that a lot of you are going to be familiar with this. If you are not, it's in your best interest to look at this. So let me just very quickly go through this. So we are going to be interested in something which is, so this is phi x, phi y. So how do you do this? So you look at, you rewrite s in the following way. You just rewrite this as an integral like this, where this a here is going to be of a form which is ax xy is delta of x minus y, and this particular operator minus del squared. Okay, so now what we want to do is then the uh, propagator kx of xy is just the inverse of this guy, and it's a straightforward exercise to show that this k is going to satisfy an equation which is just given by this boxed equation 3.29 that I have out here. Because you have rotational and translational invariance, this k of xy should only depend on the distance between the points x and y are and the modulus of that distance. And so that's and so that's why we're going to put k of xy is equal to k of r, and then we can integrate 3.29 over x. On a disk of radius r, which is centered around y. And once you do this, then what you're going to find is simply this equation out here. So you just write it in polar coordinates, and then what you find is that you're going to integrate from 0 to r some d rho of rho and times this object that we have here. So this is just the del squared written in these coordinates, where the prime is given by k prime of r is dk dr. So if you do this, what you find is this equation out here. So you're going to integrate and find that this is 2 pi g minus r into k prime of r. This is equal to 1. And then so what you're going to get is, so the form of k of r is going to be like a log of r. Okay, so this is because you're in 2 dimensions, that that you get this log of r. And so what you get at the end of the day is that phi x and phi y is given by log of x minus y squared. Now remember that from our earlier things, what we had found is if we have two fields phi of, let me not write it here, but okay. So if you have something which is phi 1 and phi 2, so these guys will only be, so these guys will be some C1 2 divided by x1 minus x2 squared, actually, right? Twice delta. So this is what we had found earlier when we were looking at two-point functions of quasi-primary fields. So this is also true in the, when you're looking at fields in 2 dimensions, this of course holds. And what happens is that this becomes twice h, um, and you have a similar thing where uh, let me write this as z1 minus z2 to the twice h, and this becomes z1 bar minus z2 bar to the twice h bar, right? So this is something that you can find out, and this is only true with if these two fields have the, so if these two fields have the same same h and h bar, this actually holds. Now you see that phi of x and phi of y give you something like log, right? And this log of x, x minus y squared. So in no way can these fields actually be primary fields, okay? So that's something that you need to keep in mind. And let's get rid of this. So what we do is we would, we just note here that these phi's are not primary fields. In terms of complex coordinates, z and z, so z and z bar, we can rewrite this. Then it just factorizes, if you wish, into a log of z minus omega and z bar minus omega bar. And now, if you look at, instead of phi of phi's, if you look at del of phi, so del z of phi with del omega of phi, now you see that this actually has a form which is 1 over z minus omega squared. So this has the right form of being a primary field. We will see that this is actually true. But for the moment, keep in mind, what you need to keep in mind through all of this analysis is that when you're looking at this 2-point function, if you look at an OPE of a del phi with a del phi, what you get is a 1 over z minus omega square piece, okay? Also notice that this is a 1 minus, sorry, z minus omega squared here. So there's a factor of 2. This OP reflects the bosonic nature of the field, right? If you exchange this phi with this phi here, this will not change what the form of the 2-point function is. So you can take it through each other, and the form stays the same. So that that sort of reflects that this is actually a boson that we're dealing with. Very good. Moving on, what you can easily find is that the EM tensor of this massless boson is of a form like this. So this is this G is nothing to do with the metric. This G is the coupling that we have. The normalization factor in front that we have. I'll just choose to keep this. So this is del mu phi minus half eta mu nu del phi squared. If you can write it in sort of complex coordinates, this actually looks much simpler. As you know, this is a CFT, so t of z bar will be equal to 0. This you can actually explicitly see from here. And also you will find that t of z is del phi, and t bar of z bar is del bar phi and del bar phi. Now, what do we want to do? I was trying to show, I was trying to just indicate to you here that, the del phi's look like something where these 2-point functions of these guys are like primary fields. So what is the way that you actually check if this particular field is primary or not? You find out what the OPE is, okay? Okay, so before we go on to the OP with the phi with the t, what I want to first show you is how do you make sense of this in a quantum mechanical how do you make sense of t of z in a quantum mechanical form? You see, there is del phi which sits at the same point z, right? So here, so what I write down here is that we need to be careful about what this means in a quantum mechanical theory, as the definition involves a product of two operators defined at the same point. So if we treat this naively, these is going to invariably lead to things blowing up. So what we usually do in such cases, for example, in your usual field theory, when you have things like this, canonical quantization, we would normal order it. Okay, we will normal order it by putting annihilation operators on the right, and this sort of guarantees that the vacuum has zero energy. We will do an equivalent thing out here. What we are going to do is, we're going to normal order this. Okay, and what that means, so, is that we are going to take del. So this is what it means. Okay, so when you are going to take z, omega going to z, what you're going to be doing is that you're going to be extracting out the 2-point function of this from here. So what is going to happen is that when you look at the so this is going to extract out the if you wish, the leading singularity between them. It'll just make sure that that thing so it would just make sure that when you are going to take z z to omega, there is no singular things which are left over. So this is how you make sense of this these two dots out here. So the normal ordering prescription is that you subtract out this guy from this. Okay. Okay. Now that you have formulated a quantum mechanical version of what T is, what I want to do is I want to figure out what the OPE of T of Z with del phi is. Okay. Now this is going to be done by something that you guys are reasonably familiar with, Wick's theorem, and let's see how this goes. Okay. So del so Tz with del phi. So we write this down first, and we write this one as well. And what we have to do is we have to make sure that we sort of contract the operators that we have here with this. So we can either do this one or we can do this one, right? So there are two options. So instead of the 2 out here, we get a 4. Okay, and we get 2 of these guys. As you know, phi of z, del phi of z and del phi of z, they can go through each other, since these are sort of bosonic fields. This is not this is not going to matter of where these are placed. So what we get at the end of the day is del of phi at z by z minus omega whole squared. The point to note is that this is at z. Okay, we are trying to find out T of z and del phi of del phi of omega. And remember, if you go back to what we were trying to do earlier, so let me just remind you of this. When we were trying to understand OPEs at the very beginning, what we said is that if we have an expression of this form, on the right hand side we are going to write things in terms of omegas, right? So now here as well, we have written things in terms of z's. We want to re-express it in terms of omegas. Okay, where did I? Yeah, so here I was. So you want to re-express this guy that I have here, this object, as something which is del phi of omega, right? So we expand this out. And if you expand it out, then what do you get? You are going to just so del phi of z. Sorry, let's just write this down somewhere. uh, Let me see if I can find a little spot. So del phi of z is del phi of omega plus z minus omega into del omega of squared of phi omega plus dot, right? So if you put this back in now, so what you're going to get is phi t with del phi is of a form like this. Notice that this has a del phi piece, and this also has a del squared phi piece. Okay. So del phi piece. So this is the operator, and there is, so this goes as 1 over z minus w the whole squared. This goes as 1 over z minus w. So now let's just let's keep this in, let's keep 3.35 in mind, and let's just go back to the form of primary operators that we had written down earlier. So this 3.24 is the form of the primary operators, right? So whatever you have, so if you have a primary operator, it's going to have a weight h. If it has a weight h, it has to be the same operator here, and that is going to be a 1 over z minus w squared piece. The other one will have a del, and it is going to be a 1 over z minus w piece. Okay, so that is, we have got something which looks exactly like that. So now you see that we have been able to actually get a form of this OPE, which is given by this. Okay, so let me try and do something actually. Okay, let's try that once more. Okay, so this is the form of the T phi OPE. Okay, so from here it should be absolutely crystal clear that phi is a primary field. Now you see that there is nothing in front of here, there is no number here, right? So the number in front of it is just 1. So this is a primary field with a weight h equal to 1, right? This was expected, right? This was expected because phi had no spin and no no scaling dimension as well. So that you can just read off from the fact that S was integral d2 sigma del mu phi and phi did not. So in 2 dimensions, the scalar will not have any. The simple scalar phi will not have any scaling dimension. And so if you're looking at del of phi, just for the fact that it has a del, it'll have a scaling dimension 1. Okay, so that's good. So del phi is a primary field with weight h equal to 1. Very good. All right, now we have a way to find out what the OPEs are. A natural thing to do now would be to try and figure out what the OPE of T of Z with itself would be. Okay, so what do we do now? So we look at trying to understand T of Z with T of omega. Okay, let me just pause and ask you guys: is this reasonably okay? So far, have you got what we did out here, right?
Just to add up on that, the fact that phi is not primary, if you try to calculate this T of Z phi OPE, then you won't have this form, right?
Yes.
That will also show up there.
That is right. That is right. So what I mean, that is an exercise that you can do. So remember, the only thing that you need to really keep in mind is in that case is just this particular piece, or if you wish, just this piece. So if you want to find out what the t with phi is, so remember, if t is del phi, goodness. Okay. So tz with phi of omega will be what? This is going to be del phi of z, with phi, or at omega. And then what you're going to do is you need to look at things like this, right?
Right.
And
Yeah.
then so what is going to happen out here, as you can see, so if you know that this guy, if you know that this guy has a form like this, so when you have something like del phi of z with phi of omega, all you need to do is you need to actually just differentiate this once. So this goes as 1 over z minus omega, right? And then you just use this, and you'll get a form of what this is. Is that clear? Pratesh, is that okay? Hello? I seem to have lost Pratesh. Hello, I'm sorry, my thing just dropped off. Hello, are you guys around?
Yes.
Yeah.
Yeah. So there was some problem with my internet. Sorry about that. Just give me a second. Huh? I'll just try and. Okay, so Pratesh, I was in the middle of trying to explain this when I just dropped off. So let me just try and do that once more. So how much were you guys? So what did you hear from me last?
Like, yeah, this tz of phi, we need to calculate del phi phi op.
That's right.
So
That's right. So the del phi OP, as you can see, if I can just make my screen all right, it's proving to be rather difficult. Sometimes Zoom can be very irritating for some reason. Yeah. So what I was trying to do is I was trying to show you that if you have this if you have the fact that the phi with phi goes as log, then that means the del phi with phi will go as 1 over z, right?
right.
And you can just plug this back in now, and then what you will see is that you're going to get a del phi of sorry. So you're going to get something which is the del phi of z by z minus omega.
Right.
And this is a z, so you need to have a del yeah, so that's the only piece that you're going to get, right?
Right.
So
Yeah.
you can work this out, and yeah, yeah, we will see this. You can work this out a bit more carefully, and then you see that this has a weight h equal to 0, and yeah, so that's something that you can do. And let me not work this out for you guys. Maybe I'll leave this as an exercise, and let me just go on to the rest of things. Very good. All right, so what we have here is, so now what we will do is we will look at the OP of T with itself. Why has this gone out of the screen? I cannot make this smaller, but anyway, so hopefully you guys can see what's on my screen. So what I want to do quickly is I want to let you, show you how to do this next thing. This is a fun thing to do. So now you have T of Z with, T of omega. And so you have now two of these, del phis at Z and two of these del phis at omega. So now what can happen? This can go with this, and this can also go with that, right? So if that is the case, so the first term, there are two ways. So the first term, there are two ways that you can do this. So you can double contract it in two ways. So you get this term. So it's either so let me see if I can draw it with something else. So it's either this. So you can either do this and that, or you can also do, for example, you can also do this and that, right? So these are two ways that you can double contract, which is going to lead you to the same answer. Hence, you have a factor of 2 in front here. And you can have 4 single ones as well. So where either this goes with this one, that's one, this goes with that, that's another one, this goes with this, that's one, or this goes with that. So there are 4 single contractions as well. So this is a factor of 2, this is a factor of 4. And now you need to put these back in, right? So as we saw, a del Z with a del omega gives you a 1 over z minus omega squared. So you have 2 of these. So you're going to get a 1 over z minus omega whole to the 4th here. Okay. And for the second one, and for this, you will not be left with something here at all, because all of these guys are gone. For the second one, you are going to have something which is a del phi of Z, which is left over from here, and del phi of omega, which is left over from here, right? So you're going to get a piece which is del phi Z, del phi omega out here, and this is going to have one piece. So this is going to have a Z minus omega squared. Is that okay? Fine with everybody? Okay, good. So let's just write this down in whole again. So what you find is you have when the dust settles, you see that the Z minus omega whole to the power 4 piece comes with a factor of half in front. And now you remember that you have to express everything not at Z, but but at omega, right? So you need to expand this one out as well. So when you expand this out, the first term is a del phi term. Then there's a del squared phi term, which comes with a z minus omega piece. Okay. So at the end of the day, what you find is that Tz with T of omega has a half into 1 over z minus omega whole to the power 4th piece. There is a T omega piece, and there's a del T omega piece. So at the outset, if this term would not have been there, then this is just a primary of weight 2, right? Since you have a factor of 2 which sits here. But this term is there. So this is no longer a primary, okay? So we immediately see that T is not a primary field in a theory of a free scalar. It is an operator, however, with weights h and h bar equal to 2 and 0, but it fails to be a primary because you have this term out here. Okay, so this is a very important thing. All right. Okay. So moving on, let's quickly do the free fermion as well. So let's say we are in 2 dimensions. Then what you have is so del so the action is given by 3.37. So this is our action. So this is psi bar gamma mu del mu psi. Remember, you were in 2 dimensions. So the Clifford algebra is as it is. If you were to look in Euclidean dimensions, so if you want to have the signature 1 1, a representation of this algebra is gamma naught equal to this guy and gamma 1 equal to this. If you didn't have if you had a sign out here, this I would actually drop off. So what happens is that if you look at this part of the action, the del naught into this gamma naught into gamma mu del mu just turns out to be this matrix where there's a del z bar piece and then there's a del z piece. So if you were to write this big psi in terms of small size psi and psi bar in a 2 component spinor notation, that is going to just boil down to an action which looks like this. So this is psi bar del psi and psi del bar psi. The classical equations of motion will be del of psi bar equal to 0 and del bar of psi equal to 0, which essentially mean that the solutions will be any holomorphic function psi of z in which is here, or an anti-holomorphic thing psi bar of z, which is for this guy. So we need to find the propagator, and as I said, this is going to be left to you as an exercise. So this is going to be psi and psi will give you 1 over z minus omega. This also reflects the fact that when you take psi through psi, take one psi through another, since these are anti-commuting guys, as you can see, this is going to this right hand side will pick a sign up, right? So that sort of reflects the fact that it's a fermion, and so that's that. You can also try you can also by standard arguments arrive at what T of z is. T of z is a form like psi del psi. And again, here this normal ordering indicates that when you take omega to z, you need to subtract out this piece. Okay. All right. So now, so you have got that. Well, you have not got it. This is left to you as an exercise. So this is what psi with psi is. So you need to find psi with del psi. So that is just going to be 1 over z minus omega again. And you can look at again playing the same games with contractions. So let me spend 2 minutes trying to explain this next one. So you want to find out what the OP of z t with psi is. So you write down what t is. So that's psi del psi, and there's another psi out here. Now what you need to do, so you have this, so you have to look at with contractions again. So the first one is psi goes with psi and the del psi is left over, and here the psi goes with del psi goes with psi, and this is left over. Now the point is, if you have to we contract two guys, you need to bring them side by side. So you need to move this del psi through the psi and onto the left. So if you have to do that, you're going to crucially pick up this minus sign. Okay, so you see from this step to this step, there is a minus sign that I've picked up in the first formula. Okay, so what you have is once you do this, there is going to be a del psi of z, and there is going to be a psi of z. Now you want to expand this out, and if you want to expand it out, then what you're going to get. So you just, I mean, Taylor expand this once and once again, and once you, I mean, do the math, you are going to see that what you're going to end up with. There is a factor of 2 which I don't like. Um, yeah, okay. No, that is fine. That is fine. So as you see that these two are of the same sign. So what you do is you write psi of z as psi of omega plus z minus omega del omega of psi, and you put that in. So if you plug it in here, so you get another piece. So what you're going to get is psi of z by z minus omega 2z minus omega is equal to psi of omega by 2 into z minus omega plus there's a half into del omega of psi. This is a squared, I'm sorry. So this is another squared. So this is z minus omega. So you see this term is going to add up with this term and is going to give you this term. Okay. So once you expand this out, at the end of the day, what you're going to find, let me just erase these guys. Um, let's see if I can trigger this at one go. Very good. So when the dust settles, what you're going to find is that psi, I mean t with psi, is going to give you a half. So this is going to be the OP, and you again see this is a primary field. The weight of this H turns out to be half, right? So yeah, I somehow didn't write this down, but let me just write this down here. Say that, okay, let's write this down here. Psi is primary with H bar equal to half 0. Okay, and you will similarly see that psi bar is a primary with weight 0 half. Okay, now you can find out the TTOP in the same way. If you find out the TTOPE, what you're going to get is this part stays the same as before, but you have something which is again a 1 over z to the power I mean z minus omega whole to the power 4, but the number that you had out here, which was half before, has turned out to be 1/4. Okay, so this is identical to the equation that you had before. As I said, the coefficient of the anomaly piece has now changed. All right. So to end this lecture, I'm going to show you what the OP of T of Z with T of omega is. So from our examples, we are naturally led to the form of the OP of the energy momentum tensor with itself, and that is given by some numbers. So this part stays the same, and there is something which we call C over 2 multiplying the 1 over z minus omega whole to the power 4 piece. C is a constant that is going to depend on the specific model that you're looking at. This is equal to 1 for free bosons and equal to 1 for is equal to half for free fermions. This model dependent constant is what is going to be called the central charge. Okay, you have encountered the term central charge before when we were looking at the central extension of the Virasoro algebra. We will show that this is one and the same. And this number turns out to be one of the most important quantities that characterizes a particular CFT. And just to end this, I would say that this number is something that you need to supply from outside. It's not determined by symmetries. We have already seen that this number is equal to 1 for free scalars. Now, if you have n number of these interacting guys, this is going to, I mean, non-interacting guys, not interacting. So if you have n number of non-interacting scalars, the central charge just adds up to give you n. And this gives a hint to the true meaning of C. The central charge is going to actually capture what the degrees of freedom in a CFT are. We will see this again and again in a more in a more clear way as we go ahead. But for now, the thing that I want to just hammer down is the fact that this particular OPE is something that you should really remember. Okay. This is a very important, I mean, OPE. This is a very important formula for us. And we're going to have a lot more to say about central terms and all in the next few lectures. But yeah, that's sort of the essence of what I wanted to do in the class for the day. Okay, good. So any immediate questions?
Like, I have a question.
Yeah, please.
So at least like for the examples which we have considered, like free boson, free fermion, like
Yes.
T bar OP will be 0.
Yes.
Okay.
That's always so. So we're going to be seeing that the T bar thing is always going to be 0. This is a sort of reflection that when you are looking, so it's a reflection of the fact that your I mean holomorphic and I mean anti-holomorphic things actually factorize.
Right. Yeah.
Okay. So that's something. So it's also, so you'll see that this is also linked up with the fact that we the symmetry algebra underlying CFT is actually these two I mean commuting copies of I mean of the Virasoro algebra, right? We will see how these are linked up. So the T with I mean T bar OP is always I mean going to be 0.
Yeah. Okay. Yeah.
Any more questions? All right. So so next time around, what we will do is we will try to go forward with this.
So yeah,
And
I have a doubt.
yeah,
Hello.
please. Yes.
So I have a doubt about equation 3.41.
3.41. What is 3.41? Yes.
So fermionic ET.
Yes.
OP. No, T psi. Okay. So from here, how can we determine this weight? Sorry.
So what you want to do is you want to find out this guy, right? So what did we say? What we said is when we are looking at the weights, so you remember that the primary fields are I mean going to be given by 3.24.
No, yeah.
Right? So the number that you have
That's
out
what
here.
I was saying that. Yeah, that's fine. That's fine. So I mean, 3.41 is looking little bit weird to me.
Why is it looking weird to you?
It seems that del psi and psi has been interchanged.
Maybe I have written something wrong. Just give me a second.
That's why I got confused.
sorry.
Maybe.
No. Oh yeah.
Yeah.
yes. Thank you, Amorto.
Okay.
Yeah, you are right. I'm well. Let me make sure that I get the. So there is no squared here, and there is a squared here. Sorry for that, and thank you for pointing this out. Okay. So what I should also clarify is that psi and del psi have been interchanged on top out here as well. There is no square here, but there is a square here. Right. So what is happening is that when you were looking at, so the del psi is the one where you're contracting psi and psi. Yeah, very good. Okay, thank you very much. So, I mean, everything was right except for the fact that I just interchanged as I mean, as was being said, I had interchanged some things. So when you are looking to contract psi with psi, you are obviously going to get a 1 over z piece, right? So that is what we found. So what is left over is this guy. So you are going to get a 1 over z z minus omega piece here. When you have contracted a del psi with psi, you're going to get a 1 over z minus omega squared piece. Okay, and the rest is as we were saying. So you have this at z, so you expand this out and you get these extra terms, and you also expand this out and get and you're going to be left with this at the end of the day. So if you get this, then the OP is of a form like this. And once the OP is of a form like this, you can read off the fact that there is a half which sits out here, and that is because it's a prime. So this indicates that psi is a primary of weight half and 0. All right, my internet is very bad today. And it has been going on and off. So yeah, I think I'm at the end of what I wanted to say. So if there are no more questions, then I will not share screen anymore. But if there are some things that you want to still ask me, please go ahead. Okay, it seems that possibly there are no more questions. If that is so, then we meet again next week. And there is an assignment that I've sent out to you guys. I have not yet put it on. Yeah, so I think I sent it out to everybody this time around. So so I'll also put it on the website. But have a crack at your assignment, and we will try and do. I mean, I'll try and also send you a little more. Some little more stuff, mainly regarding weak contractions and all of that, and I'll try and do this maybe by the end of the week or something. Okay. And remember that you are supposed to present. I'm supposed to send you an email about that. So 20th October, everybody is going to have 5 minutes to give us an idea of what is happening. Okay, in your projects. For those of you who are going to be marked on this course. All right. I'll send an email out for that as well. Okay. So, all right. So if there are no more questions, which I don't think there are, I will end now, and I'll see you guys on Monday next week again. Bye-bye.